Hey guys, welcome back to my YouTube channel. So in this lecture, we are going to continue our discussion on the things in digital electronics. So thing is that the overflow will occur in the case where when two positive numbers are added and the result is negative, and vice versa when two negative numbers is added and the result is positive. So in both the case, the overflow will occur. So now the condition is that when two negative numbers are added and the result is positive, and two positive numbers is added and result is negative. So this is the case in that particular system or in that particular arithmetic, there is an overflow occurring. So if overflows occur, then we need to take into account that we need to increase the number of bit to represent that particular number. So that is the thing we need to take. So there is second one example, that C in and C out. If we take XOR of that one, so that is equal to 0, then overflow, no overflow. If that is equal to 1, there is an overflow. For an example, if we add 1 1, if carry is the C in, so this is what the C in we represent. If we add this one, this is 2, so 2 can be represented as 0 1. So if you think the C in and C out, which is both are same, so if we XOR 1, then which is equal to 0. So if 0 is there, then there is no overflow. So there is no overflow in the system. So this is how the thing that we need to take into account. So if the thing, if here it is 0 and here it is 1, then there is an overflow in the system. So let me have an example. If n which is equal to 4 bit, so if we take the summation which is 0 1 0 0, which is 4, and this is 2's complement representation, so it is 0 1 0 0. Since both numbers is positive, I am directly representing their 2's complement, I am directly representing their positive entries only. So if we add this one, this is 1, this is 0, and this is equal to 0, and there it is 1. If you see, the C out is equal to 0, but here carry is 1. So if we XOR this one, 1 XOR 0, then this is 1. Here you can see there is an overflow in the system. So how we are saying the overflow is that if we add this number, the number is 9. But in 2's complement representation, the range that what we can max represent is from -8 to 7 only. So in this range, the 9 cannot be represented. So that's why it is indicating that there is an overflow in the system. So this is how we will be representing how we can take into system. So even if we consider this in a normal 2's complement addition, based on the second rule, if there is no complement, then the answer is negative. So from our case, we know the answer is negative. So when we add two number and answer is negative, then that is also a condition for overflow. So we have added two positive number. This is 2's complement representation. So we are taking this as a 2's complement. So that's why when we add two positive number and the result is negative, then this is also a condition for overflow. So let me take another one example where 4 plus 3. So 4 can be represented as 0 1 0 0. 3 can be represented as 0 0 1 1. Here if you see, if we add 1 1 1 1 0. Here if you see, here there is nothing carry, and here also no carry. So when 0 XOR 0, which is equal to 0. So here we can clearly say there is no overflow. Because the number, the result is 7. So 7 will come in this range, but 9 will not come in this range. So here it will come. So we can detect the overflow by using this terminology or this logic. So this is the only thing that we need to represent making use of it. So if we find out the numbers, it is 2's complement addition, right? So if there is no carry, then we will get the number which is equal to -7. But only if we use the next 5 bit number, then only we will be getting, this is with 4 bit. So if we convert this one, if we convert this to that normal thing, we will get that only, because here that is the answer we know. If there is no carry, we have to think that number is negative and we have to take 2's complement of this. So if we take 1's complement, that is 1 1 0, and if we add 1, we know that the answer is 0 1 1 1. So this is 7, so which is -7. So if we use the 5 bit representation, then only we will be able to get the exact number. So if we use 5 bit, then there is no overflow in that. So then the number is 8 plus 1, that is 9. So then only we will be able to get the positive number. So we have to increase the system, then only we can avoid overflow. So overflow is one of the very important concept while handling bits and data representation. So I hope you guys able to get the concept in the overflow. So from this understanding, we have completed all the basic stuffs of all the things. So in the next stage, what we have to discuss is the fixed point representation. So fixed point representation, which is similar to BCD, radix, or all kind of representation of decimal number, similar to that, fixed point is also one kind of representation. So here we will be using 32-bit number to represent any number. So first bit, which is for sign, and which is signed, which is for 121, and then integer part is where the integer part can be represented with 23 bits, and the fraction part which will be represented with 8 bits. So total if we add, that is 32 bit. So this is fixed point representation. So this is, there is no change. Every part will be represented like this. So if the number is greater than 23 bit, then we can't represent that using fixed point representation. So there is lot of demerit with the fixed point representation. So in order to overcome that, now we are going to use floating point representation. So this is one of the IEEE standard that they gave. There is a floating point representation. So which will sort out many problems in data representation. So which is one of the dynamic and also scalable. So okay, this thing how it will work is the sine into Mantissa. I will explain all the things, so don't worry. Sine into Mantissa into 2 power plus or minus exponent. So this is the format that they used to represent the floating point representation of the number. So here let us use the direct example so that you guys won't able to understand this one. So the normal thing we can represent the 32 bit, which is called as single precision. 64 bit will be called as double precision. So all our system will use 64 bit processor, right? So that are double precision. So single bit, so our single precision, S is 1 bit, and the exponent, which is 8 bit, and the significant, which is 23 bit. So like this way, this will be summation to 32. So this is exponent. So exponent part has that bit, that 8 bit. So here I will be explaining with a number, with a sample number, so that you guys will be able to understand it. So 52.21.875. So we are going to represent this decimal number in floating point representation. So let's convert this into a decimal part, which we know, right? So in order to convert that into binary, we need to repeatedly divide this by 2. So I'm leaving this part to you. So I'm directly writing the answer here. So if we convert that into binary, we will getting 110100.00111. So that will be the answer here. So we need to move this point to the first precision. So 1.1010000 and then 31 into 2 power 5. So we have moved 5 parts, so that is 2.5. So here this part is right. So this part is called as the normalized significant. So this is called as significant. Okay. This one, this 5 need to be equalized to E minus 127, which is equal to 5. So E, which is equal to 132. So let's take the thing. So let's have a sign bit. So sign bit, exponent, and significant. Okay. So sign bit is 1. As the number is positive, so we can ignore this. That is directly equal to 0. The 8 bit, so that is need to be taken care. This 8 bit is representation of the exponent part. So we have to take the binary equivalent of this, and we need to represent that in this one. So 1 0 0 0 0 1 0 0. So this is equivalent to 132. So that decimal, that binary conversion we have done. The significant part is same like this one, the exact this one. So 1 0 1 0, that thing. So we need to represent that with 23 bit. So 1 0 1 0 0 0 0 1 1 1, and then rest all are 0. So 0 0, so 0 0 3 6 9 12 15 16 17 18 19 20 21 22 23. So this is 23 bit, this is 8 bit, this is 1 bit. So this is the single precision representation. So here we can write single precision representation of the number in floating decimal point. Single precision representation. So this is one of the very important thing. So similarly, we can able to find for 64 bit and 16 bit any kind of representation we can convert. So here when it is a double precision, we know that we will be having 64 bit representation. So I hope the representation is understood for you guys. So that is very simple. We need to convert that into normal binary manner, and then we have to move the fractional part there, and based upon that we can able to represent sign bit, exponent, and significant. The sign bit will be 1 if the number is negative, or else it will be same positive. Okay. So double precision we have 64 bit to represent. So sign bit, exponent, and significant. So sign bit is as usual 1 bit, exponent is 11 bit, and significant is 52-bit. So we can represent even large number. So let's take an off precision. Off precision is means that is a 16-bit off precision. Same sign bit is 1, exponent is 5-bit, and significant is 10-bit. So total which is equal to 16 bits. So 16-bit representation. So this is used for scalability. So there is many purpose like double precision, off precision, single precision, and many kind of things can be represented with things. So this is why the floating point representation is one of the very important representation that latest in IEEE standard. Like I think IEEE 754, that is one of the documentary that they have released. Even you can see the document presentation from the official IEEE IEEE page. So IEEE I think 754 only. 754. So there will be 32-bit single precision representation they will be giving. So from there you can able to understand all these document things there. So I am suggesting you guys to go over and see this if you guys have a free access over it with your college mail IDs. So this will give you some idea. So I hope you guys able to understand all the things in a number system. So number system is coming to an end here. So we have completed all the things in a number system. So in the next class we'll be seeing about logical gates like Boolean, algebra, and K-map, those things in there from next class. So please stay tuned, like, share, and subscribe to the channel, guys.